Good morning, class. We are looking at Chapter 2, Limits, Section 2.3, Limits of Functions at Finite Numbers. So we looked at limits of sequences, limits of functions at infinity, limits of functions at finite numbers, and now limits of functions at finite numbers we are looking. So here's the summary of what we have already covered. A sequence is an ordered list of numbers, or function f whose domain is the set of natural numbers 1, 2, 3 to infinity. Limit refers to the long-run behavior of a sequence, i.e. what happens to a sub n of a sequence in the long run. The limit of a sub n as n approaches infinity equals L. We say that a sub n converges to L. Limit of a sub n as n approaches infinity equals infinity or negative infinity or does not exist. We say the sequence diverges. To find limit, simply plug in and observe. Now, there are some theorems that we're going to look at. The limit of 1 over n to the power of p as n approaches infinity is 0 for p larger than 0. The limit of r to the power of n as n approaches infinity depends on the value of the base r. If it's between -1 and 1, is 0. If it's 1 is 1, and if it's larger than 1, it's infinity. Therefore, a geometric sequence, we add up summation of a r to the power of n minus 1 as we go from 1 to n becomes a geometric series, and their sum is a times 1 minus r to the power of n over 1 minus r. If r is between -1 and 1, r to the power of n goes to 0 according to this theorem, and this limit simplifies to a over 1 minus r. In other words, the limit does exist, and it converges to a over 1 minus r. A geometric sequence has an equation b sub n plus 1 is r b sub n recursively. B sub n equals b sub 0 r to the power of n explicitly, where b sub 0 in some text they use a instead. If we add a constant, such as giving medication, the constant amount of a medication at a specific time step to a patient, b sub n plus 1 is r b sub n plus c. The solution becomes the same thing that we had here, and it adds this piece. So b sub n becomes b sub 0 r to the power of n plus c times 1 minus r to the power of n over 1 minus r. And again, a or b sub 0 are the same. And also we discussed horizontal asymptotes. If the limit of f of x as x approaches negative infinity or positive infinity is L, the line y equals L represents the horizontal asymptote, short HA. Now, section 2.3, limits of functions at finite numbers, finding limits by numerical and graphical methods. Definition. Again, we've already see that this is how we read it. The limit of f of x as x approaches a equals L. Let's look at a couple of graphs. All three, as x approaches a from the left and right. From the left, we are in this portion of the graph. From the right here. From the left, you approach L from the bottom. From the right, you approach it from the top. In all three cases, the limit of f of x as x approaches a exists, and it's equal to L. What's the difference? Well, if you look at this one, there's no hole, so P, the f of a is also L. In part B, f of a, the solid point has the y coordinate b, which is not equal to L, makes it discontinuous at x equals a. And this one, f of a is not even given because there is no solid point. It's undefined. So those are the three cases. Part A, f of a equals L. Part B, f of a equals B, which is different than L. Part C, f of a is not defined, but in each case, regardless of what happens at A, limit of f of x as x approaches A equals L. It's important to understand the limit means close to L, close to A in this case, not at A. If you understand that, pretty much the concept is understood. One-sided limits. The limit of f of x as x approaches A from the left. This notation means A from the left. That means a little bit less than A equals L. The limit of f of x as x approaches A from the right is L. This means a little bit larger than A to the right of A. If the two are identical, the limit of f of x as x approaches A equals L. Finally, definition of a VA, short for vertical asymptote. Limit of f of x as x approaches A, or A from the left or A from the right, if it's either negative or positive infinity, gives rise to the equation x equals A being the vertical asymptote or of the graph. All right. Finding limits by numerical and graphical method. Guess the value of the limit of x minus 1 over x squared minus 1 as x approaches 1. And we are also going to do the algebraic or analytical method as well. So this expression, we're going to call it f of x. F of x is x minus 1 over x squared minus 1 is not defined when x equals 1, does it matter? And it's important to understand that if you plug in 1, it doesn't work because the denominator is 0. In fact, it's 0 over 0, which is indeterminate. But does it matter? The answer is no, because we are not saying x equals 1. We are saying x is approaching 1. So for the numerical method, let's evaluate the function, however many decimals they ask us, for values of x that approach 1 but are not equal to 1. So we're going to make up some tables below, give values of f of x for values of x less than 1 and x larger than 1. So x is less than 1, here's the function, and less than 1, let's say fairly close, 0.5, 0.6, 0.7, 0.8, 0.9. Even 0.9 is not good. 0.99 and even more nines. So even 0.9 is way too off. Okay? So you evaluate this function and you get the following table. And you notice the numbers seem to be closer and getting closer and closer to some number. That is the limit. That number, it appears to be 0.5. Let's try it with the right side. 1.9, 1.8765432, even 1.1 is not good. So 1.01, 1.001, 1.000. And you get those values. And by the way, you can add more nines here, you can add more zeros in between to get closer. And if you look at the trend, we seem to get to this number. And as you can see, this number approaches 0.5. This number also is approaching 0.5. So we say the limit of x minus 1 over x squared minus 1 as x approaches 1 must be 0.5 numerically. We can graph the function graphically as x approaches 1 from the left and right. From the left, we are in this branch. From the right, we are moving in this branch towards the same hole, having the y coordinate 0.5. And I'm going to remind you, when you graph any rational expression, the very first thing you must do is to put it in its lowest term, because what makes the denominator is a vertical asymptote, equation of a vertical asymptote, as long as there is no common factor between the top and the bottom. However, whatever makes the denominator is zero is not part of the domain. It creates a hole in the graph. More importantly, let's look at an algebraic approach. And you know it's 0 over 0 if you plug in. So you need to use your algebraic technique, the algebraic technique in this case, reminding you that a squared minus b squared is a minus b times a plus b, which means this is x squared minus 1 squared. So this is x minus 1, x plus 1. That's the meaning of it. The common factor of x minus 1 is dropped. And if you plug in 1, now you get 1/2, of course, the same as 0.5. So we looked at it numerically, graphically, and more importantly, algebraically. You should always go with an algebraic approach unless they ask you otherwise. Always go with algebraic approach, everybody. One-sided limits. The function h is defined by h of t is 0 if t is less than 0, and it's equal to 1 if t is larger than or equal to 0. This is called Heaviside function. It's used in electrical engineering. So the limit of h of t as t approaches 0 from the right is 1. The reason why is because for the right side of 0 has to be larger than 0. In other words, the symbol x approaches a from the right means that we consider only x larger than a, limit of f of x as x approaches a from the right. And in this case, it's 1. On the other hand, limit of h of t as t approaches 0 from the left is 0 because we consider t less than 0. So the symbol x approaches a from the left means that we consider only x less than a, limit of f of x, as x approaches a from the left. Because the two are different, the limit doesn't exist. So the limit of h of t as t approaches 0 does not exist. Also, equality gives rise to the functional value. Note h of 0 equals 1 because of the equality. If we were to graph it, this one, y equals 0 is the x-axis, in this case, the t-axis, and y equals 1 is this horizontal line. Of course, it ends at 0. In this case, we have a solid point here. So it's a half line. In this case, the point is not solid. This is also a half line. So this half line, the endpoint is included. This one is not. And so here's the definition of a one-sided limit. The limit of f of x as x approaches a from the left equals L. The limit of f of x as x approaches a from the right equals L. That means limit of f of x as x approaches a exists, and it is equal to L. Example 2, given the graph of a function g, state the values if they exist of the following. And you look at this, we really are interested in limit of g of x as x approaches 2. And then we're going to look at one-sided limit to figure this out. So limit of g of x as x approaches 2 from the left, 2 from the right, to see what happens here. This is of interest to us. So from the left, here's number 2. From the left of number 2, we approach it this way, which means we are moving towards this point. The y coordinate is 3. Limit of g of x as x approaches 2 from the right. So here's the right side of 2. Here's the branch we are moving towards this point, which has a y coordinate 1. Since they are different, the limit of g of x as x approaches 2 does not exist. We are interested in limit of g of x as x approaches 5. That's why, again, we look at one-sided limit, the limit of g of x as x approaches 5 from the left and as x approaches 5 from the right. So notice number 5, here's the left and right of number 5. From the left, we move this way towards the hole. From the right, we move this way from the hole. So both sides, we are moving towards this hole, which seems to have a y coordinate of 2. And because the two are identical, the limit of g of x as x approaches 5 equals 2. Now, I want you to notice the following. If we look at this solid point and the y coordinate is 1.4, that means g of 5 is 1.4. And of course, is not equal to the limit. So the limit and the functional value are different. Later on, we discuss the concept of a continuity. The function is not continuous at 5. Also, if you look at 2, we don't have a solid point. Therefore, g of 2 is not given, is undefined. And again, later on, we discussed that this is a jump. It's a discontinuity. There is nothing we can do, but this is a removable discontinuity. We can fix it by redefining the functional value as the limit, equal to the limit. Let's look at another graph. Here's the graph we want to look at. And again, we are interested in limit of f of x as x approaches 2, but we're going to look at one-sided limit. So limit of f of x as x approaches 2 from the left, limit of f of x as x approaches 2 from the right. We locate number 2 along the x-axis. So from the left side, we use this branch, which gives us this point. We are moving towards that point with the y coordinate of 3. Now, the limit of f of x as x approaches 2 from the right. 2 from the right is this way. We are moving towards this hole, which has a y coordinate 1. And again, they're different. One-sided limits are not the same. The limit of f of x as x approaches 2 does not exist. F of 2. Well, you look at x equals 2, look for the solid point, which is here, and has the y coordinate 3. That's your answer. F of 2, that means x exactly at 2. What is the y coordinate? Limit of f of x as x approaches 4. So number 4 is here. Approaching it from both sides. From this side, you approach this way. From that side, you approach this way. And both of them seem to be getting to this hole, which has a y coordinate 4. Therefore, the limit of f of x as x approaches 4 equals 4 because one-sided limits are identical. Now, nevertheless, f of 4, there is no solid point. It's undefined. It's not given, which makes the function discontinuous at 2 as well as 4. But 2 is a jump. There's nothing we can do to fix it. 4, because there is a hole only, it's a removable discontinuity, we can fix it. That's what we will discuss later. Infinite limits. This definition is illustrated graphically in the following figures. So, what do we have? If you look at these two cases, both of them, see what they give us. This one, the limit of f of x as x approaches a is infinity. Whether we approach a from the left or right, in both cases, it blows up to positive infinity. On the other hand, in this case, as we approach a from both sides, the limit of f of x as x approaches a is negative infinity, known as infinite limits. Similar definitions can be given for the one-sided infinite limits. So if you look at all of these cases, those are one-sided. For example, this one, limit of f of x as x approaches a from the left is infinity. In this case, limit of f of x as x approaches a from the right is infinity. In this case, the limit of f of x as x approaches a from the left is negative infinity. It's going down. And in this case, the limit of f of x as x approaches a from the right is negative infinity also. And so in all those cases, x equals a is the equation of a vertical asymptote. In other words, if the limit of f of x as x approaches a, or a from the left, or a from the right is either negative or positive infinity, the line x equals a is the vertical asymptote of that function. That's a precise definition of a vertical asymptote, everybody. For example, everybody is familiar with the basic function y equals ln x. In fact, y equals log x base a, where base a is larger than 1. Looks similar to that. And clearly, we should know the graph, and we should know from the graph, we can get a lot of information. For example, obviously, the x-intercept is at 1, 0. The domain is 0 to infinity. The range is negative to positive infinity. And there is no y-intercept and so forth. At the same time, we notice this means what? The limit of ln x as x approaches 0 from the right is negative infinity, meaning the y-axis, or x equals 0, is the vertical asymptote. All right. We are given a graph. We want to find the limit or of r of x as x approaches 2, 5, negative 3 from the left, negative 3 from the right. And reminding everyone, and we want to find equation of vertical asymptotes, reminding everybody of the definition we just discussed in the previous page of vertical asymptotes and what they are. So having said that, let's start with number 2. As we approach number 2, from the left or from the right, in both cases, it's going down, and the answer is negative infinity. 5. As we approach 5, from the left, from the right, Makes no difference, both goes up to positive infinity. Now, limit of r of x as x approaches negative 3 from the left means this way. And this way, it's going down. The answer is negative infinity. On the other hand, the limit of r of x as x approaches negative 3 from the right the answer is positive infinity. And so it gives the equation of vertical asymptote in this case as follows. Over here indicates x equals 2 is a vertical asymptote. Over here says x equals 5. This one says x equals negative 3. This says the same thing, x equals negative 3. Therefore, the vertical asymptotes have the equations x equals 2, x equals 5, both refer to x equals negative 3. Those are the vertical asymptotes of the graph. We're going to find the following limits. The limit of the square root of x plus 4 minus 2 over x as x approaches 0. So we're going to plug in. If I plug in 0 here, I get 4. Square root of 4 is 2. 2 minus 2 is 0. The bottom is 0. So we get 0 over 0, which is an indeterminate form. So what is the technique? Because the numerator has a square root, the technique is to multiply by its conjugate. The conjugate, you write the same thing, you just change the sign. If it's negative, you make it positive. If it's positive, you make it negative. So it's 0 over 0. We multiply by it. However, you can't just multiply by that. You also have to divide by it because you have a right to multiply by 1, nothing else. So you multiply and divide by the conjugate. First and foremost, the denominator, you leave it as a product. Remember, x is approaching 0. It is the 0 in the denominator that is a problem. So you keep them as a product. You do not distribute. Secondly, the numerator, we remember a minus b and a plus b are conjugates. Their product is a squared minus b squared is one of those identities. And therefore, this one will give us square root of x plus 4 quantity squared minus 2 squared. So we use the identity to come up with the answer. And so x plus 4 comes out, then minus 4. 4 and negative 4 cancel each other. X and x cancel each other. We get 1 in the numerator. If we plug in 0, we get the square root of 4, which is 2. Plus 2 is 4. That is the denominator. The numerator remains as 1. The final answer is 1/4. By the way, the numbers that you see, they refer to the practice test that is posted under the module of Canvas for this exam. So the limit of x plus 2 over x plus 3 as x approaches negative 3 from the right, in this case, the same thing as x approaches negative 3 from the left. So first and foremost, if we ignore from the right and left, just approaching -3. The top becomes -1. The bottom becomes 0. First, let me discuss the top. The top, if you are approaching it from the left or right, makes no difference. It's very close to negative. If you approach it from -3 from the right, that becomes like negative, let's say 0.99. Whereas from the left, that becomes like negative 1.001. Nevertheless, it's just -1. It makes no difference. 0 is the only number you want to be careful. When you divide by 0, we used to say it's undefined, but that's not the case. It's either positive or negative infinity, and we need to figure it out. The reason you need to figure it out in the fashion that I'm going to go over is very simple, because every number let's pick a number, 7. The left is positive, so is the right. This is like 6.9. This is like 7.1. But if you go with -7, the same thing. Both sides is negative. Negative, negative. This is the left side is negative 7.1. The right is negative 6.9 as an example. However, 0 is the only number that the left side is negative, the right side is positive. So you need to figure it out, and you plug it in. Again, for the numerator, doesn't make much of a difference. If it's a positive number, both sides positive, negative, both sides is negative. So the numerator, if you want to pick a number, -3 from the right, like -2.9, and you add +3, right? And you get, and I'm going to emphasize, positive 0.1. You can even write -2 + 3 is positive 1. The point is 0 from the right, because this is positive. On the other hand, here, if you plug in -3 from the left, like -3.1 + 3, which is -0.1. So this time, -1/0 from the left. So what is the difference? Negative over positive, negative. So it's negative infinity. Negative over negative, positive infinity. That's how you figure out when it's 0 in the denominator, whether you have a positive or negative infinity. All right. The limit of e to the power of x over x minus 5 quantity cubed as x approaches 5 from the left. So if you plug in 5, you get e to the power of 5, 0 cubed, which is 0. And again, 5 from the left or right, it makes no difference for the numerator. E to the power of 4.9999, or even if it was from the right, e to the power of 5.00001 would be exactly the same thing, and it's a positive value. When you divide by 0, it's going to tend infinity or negative infinity. You have to figure out which one. So is it 0 from the right or 0 from the left? Let's figure it out by picking up a value. X is approaching 5 from the left. 5 from the left, like 4.9. That's what we want. So 4.9. Or even 4 minus 5 is -0.1. We are interested in the sign. So we're going to write e to the power of 5 over 0 from the left cubed. Now, what happens when you raise a number to a power? If you have, let's say, negative 3, and you raise it to the power of even, becomes positive 9. But if you raise it to the power of odd, it remains as negative. And number 3, let me use a different color. Number 3 is an odd number. Therefore, negative to the power of odd remains as negative. Also, e to the power of 5 over 0. It's infinity, but now that we know the sign, we know precisely it's negative infinity. To make some sense out of this, let's look at the same question. However, change the exponent to any number you want, but even this time. So the point is, the number that we are using here is even. So we have same situation to the power of 4. And because it's even, this means 0 from the right, and therefore is positive infinity. That is something you want to be careful of. They seem to be identical. In this case, the exponent of 3, which is odd, results in 0 from the left and therefore minus infinity. In this case, the exponent of 4, which is even, results in 0 from the right, which is positive infinity. Let's erase my work. We are interested in the limit of x squared minus 2x over x squared minus 4x plus 4 as x approaches 2 from the left. So if you plug in 2, or from the left or right, 2 squared minus 2 times 2 is 0. 2 squared minus 4 times 2 plus 4 is 0. So you get 0 over 0, which is indeterminate. When you have a fraction, more specifically, a rational expression of 0 over 0, the technique for the limits is to use factoring. So the numerator is easy. You just take the x out. But I want to remind you of some identities. A squared minus 2ab plus b squared and a squared plus 2ab plus b squared, those are perfect square trinomials, which means the first one is a minus b quantity squared, and the second one is a plus b quantity squared. So the top is simply x times x minus 2. The bottom follows this one, the very first one. So it's x minus 2 quantity squared. We can drop the x minus 2 from the bottom. We can drop the exponent from the bottom and x minus 2 from the top. And now if I plug in, it's important to know if I plug in 2, I get 2 over 0. Same situation. The top is some number. The bottom is 0. And therefore, it's going to get to infinity or negative infinity. We don't know yet. We have to figure it out. To figure it out, 2 from the left means like 1.9 minus 2 is minus 0.1. So it's 2 over 0 from the left. You know the answer is infinity. However, because the denominator is 0 from the left, that means the answer is actually minus infinity. And that's important to know. Negative infinity is the final answer.